Hi there. Today I'd like to talk about the vapor pressure of a pure substance and how it depends on the applied pressure on that substance. In particular, let's focus on a liquid, pure liquid substance, and how the vapor pressure of this liquid will change as we change the pressure applied to the liquid. So graphically, right, what we're saying is that imagine having a container in which you have a pure liquid, say water, as an example, right? Pure liquid water in equilibrium with the gas phase. So we're going to have liquid water in equilibrium with the gas phase, and then suppose that this container is closed, or in other words, that there is a total pressure being applied to this liquid, right? So you may imagine, right, some sort of force, right, on that container to the extent that it allows for equilibrium between these two phases to exist, liquid and gas. Certainly, if this pressure is huge, right, if we squeeze this volume that much, then eventually all you will have is liquid, right? So, but if the external pressure is such that it's equal to the vapor pressure of the liquid, then we have an equilibrium of the two phases, right? So what we are trying to discuss today is what happens if the pressure on the applied liquid changes because you have, in addition to molecules of water in the gas phase, molecules of other species in the gas phase, right? So in other words, in this particular situation, what we can say is that the vapor pressure of gas, of water in this case, right, is equal to the external pressure, and is equal then to the total pressure, right, exerted on the liquid. But now let's imagine a different situation. Imagine that we now add a gas, in a container. So I will draw it now here. So what is changing is that in addition to the gas phase of the pure substance, you have other substances, let's say plus helium gas, right? We have not changed this mass here. So the total pressure that is being exerted on this liquid is equal to the total pressure that is being exerted on this part. The difference is that the contribution to that total pressure from water is different from the contribution that it made in this example. In this example, the total pressure is due to just water in the gas phase. In here, the total pressure is different, right? So in other words, the vapor pressure of water is now a partial pressure, as opposed to total pressure. It's partial pressure, right? So we want to know how that pressure of water in the gas phase is going to change as a function of the total pressure exerted on the liquid. One way to visualize it is by adding other molecules in the gas phase, so that will change the partial pressure of water, which translates into different vapor pressures for water. Okay, so this is the graphical representation of our ideas. Let me erase that now, because I'm going to discuss the equations that will be useful to calculating these properties, these changes. Okay. Okay, so our goal now is to get here, this equation, and identify the assumptions that are made in getting there. Okay, so to derive this, let's see what is our thermodynamic function, the function that is really useful for this kind of purpose. And that is going to be the chemical potential. We know that the chemical potential of the liquid must equal the chemical potential of the gas for them to be in equilibrium or in coexistence with each other. So that means if the chemical potential of the liquid at some T P value is equal to the chemical potential of the gas at some T P value, then they are at equilibrium, in coexistence. So liquid and gas, right? Also, if there are changes in the chemical potential, right, then those changes have to be of the equal magnitude in these two phases so that they remain at equilibrium. In other words, the mu liquid should be equal to the mu gas if they are to remain at equilibrium, right? So if you guys remember, the mu liquid at constant temperature, if we want to keep this at constant temperature, the mu liquid is going to be equal to, see if you guys remember, what is the mu in general for a function of T and P? The mu in general. All right? See if I put it here for you guys. The mu is equal to minus Sm dt plus Vm dP, right? I hope you guys remember this relationship, right? So because this is going to be at constant temperature, after all, we are interested in changes of the applied pressure at fixed temperature, right? So this guy is no longer there. So the mu of the liquid is going to be Vm dP, and the P is the pressure applied to the liquid. So now let's go back to our equation here, or our derivation, so that you don't get confused. I will delete this. Okay, since we know what we're talking about. So this part here then is going to be Vm of the liquid, right? Vm dP. But please keep in mind that this is P. The equivalent of this blue P is the P applied to the liquid, equal to Vm gas dP, and this is the P of the vapor pressure of the gas. So these two P's are not identical, okay? So with your permission, I'm going to make a difference between these two guys, right? The difference, to be consistent with our final result, is that I will use blue here for this P. That's the applied pressure to the liquid, okay? So now you know what we're saying here. Now, we are interested in the vapor pressure of the gas as a function of the pressure applied to the liquid. So let's do dP, dP. Right? So then dP, dP, right, is at constant temperature. And now you see why I want to have different colors here, right? dP, dP you say is 1. But now remember, it's dP, how the vapor pressure of the gas changes with changes in the pressure on the liquid. So then it's dP, and I will use this blue here, P dP. Now you know. So this is going to be equal to Vm of the liquid over Vm of the gas, right? So dP. So that now is looking very similar to this part here. What do you guys think has happened after this point so that I arrive here? Well, as you can see, we have some RT here. That seems to be related to the ideal gas. So that's the assumption. Assuming that in the gas phase, the substance behaves according to the gas law, then I can replace Vm gas with RT over P. Okay? So again, starting from here, or following this derivation here, I will erase this part. And move this on top. So we have dP equal EM liquid, EM gas, right? You have the blue here. We already know what that means, right? And this is the step where the assumption that the gas behaves as an ideal gas law, or as an ideal gas, applies. Liquid. The molar volume of an ideal gas is RT over P, so the green P, right, the vapor pressure of the gas. And then what follows then is solving for our unknown. And our unknown is this P here, the vapor pressure of the gas as a function of the blue P, right? So then this goes into P over P equal Vm liquid, V, and then blue P, right? And then we have an integration of this, right? And this, the vapor pressure could go from some 0 to, some initial value, P sub 0, or reference value, P sub 0 to some P. And when the applied pressure is going from 0 to, let me use the blue P there, so we use the P prime to distinguish these two things. So in other words, imagine the picture when you have the pure molecules of pure water in the gas phase. That would be the equivalent that you are not exerting other pressure or additional pressure. That would be like 0. And then if you add helium or argon or any other substances in the gas phase, then it's no longer 0. It will go to some value of P, right? And then if you solve for this, I'm missing the RT here, right? VML over RT. Solving this leads you to this result, right? Which is the desired relationship, right? Because the integral of dP over P is the prime here because of the P symbol here. The integral of this is going to be ln P over P naught, or over P sub 0, equal VML over RT assumed constant over this pressure range. Then it's going to be just delta P, or delta P prime, which goes from P. Oh, this is the limit of integration that is inconsistent. P0, right? Right? It's not 0, it's P sub 0. That is the vapor pressure of the pure substance in the absence of helium or neon or argon, so whatever was there, that's P sub 0, right? So these two are equal. And then this is the total pressure on the liquid. And this is the vapor pressure or the partial pressure of the gas under these new circumstances when you have added other substances. Okay, so now this starts making sense. ln P over P sub 0, liquid over RT, the molar volume of the liquid over RT, and then delta P, and delta P is P minus P sub 0, P minus P sub 0. So you will, if you need to solve for P, then this is the equation. You need information about the molar volume of the liquid, the temperature of the experiment, and the total pressure applied on the liquid, and the vapor pressure that the system has or the substance has in the absence of any other contributors, right? Great. Thank you very much. And this is going to be important for one of the take-home questions that you need to turn in next week. OK, thank you.